Good afternoon. I'm Yu Lin from Brandis Lab. It is my great honor to present our work, P-KNN, a mathematical framework that joint calibrate multiple pathogenicity prediction tools. Before the presentation starts, I would like to pose two open-ended questions. And the first one is, what's the most practical way using multiple variant effect prediction tools in clinical practice? And the second is, how to extract stronger and more accurate evidence from the calibrated predictions. Okay, let's start the presentation. And first part, I will show the result for multiple variant effect prediction computational tools. As we are all familiar with, a computational tool assigns a prediction score to each genetic variant. And in order to use this prediction score into the framework of ACMG guideline, which the annotation is based on its probability of a variant is causing a disease, we need to calibrate these scores into a probability format. And thanks to Klingen's fantastic work by Pejava et al., now we can query a labeled dataset of multiple genetic variant. Like here, the red one are pathogenic variant, the blue ones are benign variants. And for each score of a computational tool, we can find a group of variants around that score and then calculate what's the proportion of red dot within this window to be the probability of pathogenicity. Thereby, we can map each score to a posterior probability, and the tool is calibrated by itself. But in real practice, we have multiple tools, and the current Klingen's calibration only work for a single tool. And within the same paper, it suggests that it is reasonable to choose any tools to use as long as it is chosen before seeing its score, and preferably any other evidence. So this is basically for statistical integrity. However, pre-committed to one tool, it's ultra difficult in practice. It's basically due to two reasons. The first one is we don't know how to select a tool blindly because there are no principal way of choosing a tool. And also because these scores are annotated by default, so we sometimes inevitably see multiple prediction tools result, and we tend to use the highest evidence. And moreover, even if we can strictly follow the Klingen's suggestion, because we currently encourage reanalysis for whole genome sequencing or whole exome sequencing data. But because in the initial analysis, we have seen some evidence and some result, so in the reanalysis, we cannot switch between tools in order to maintain the statistical integrity, which is impractical. And the second main reason is sometimes we might trust several tools to an equal extent and want to reference them simultaneously. So based on these motivation, our answer will be, why not calibrate them together? And the idea is actually a very simple extension from the Klingen's calibration method. In Klingen's method, we use a one-dimensional score to find the variance in the neighborhood. And now, if we have multiple tools, we use each tool's score to define a dimension and create a multi-dimensional space. And for a variant of interest, we use a sphere in this multi-dimensional space to define the neighbor. And after this neighborhood is defined, we can use exactly the same proportion to calibrate and to calculate the posterior probability. But there are some pre-processing necessary. So for example, because each tool have different scale, so before we can joint calibrate them, we have to do ranking normalization to standardize the scale of each tool. And also, because each tool have different power to discriminate pathogenic variant from benign variant. For example, here, tool 1 seems to separate red dot and blue dot better than tool 2. So we try to calculate the mutual information between the score and the dot color, and then scale each score with that mutual information. So now in this pre-processed multi-dimensional space, we can finally create our sphere and define the neighborhood and do the calibration. To evaluate if this joint calibration really works, we define two parameters based on the Klingen's definition and ACMG guideline. The first one is evidence strength, and it is basically the log likelihood ratio of Bayesian updating from prior probability to posterior probability. So in this violin plot, it basically shows how strong the log likelihood ratio is for pathogenic variant in the test dataset and benign variant in the test dataset. And the second parameter will be, is the calibration in a good quality? To evaluate this, we bin the posterior probability into 10 bins. And within each bin, we calculate the variant finally falls in that posterior probability range and see what's the frequency of pathogenic variant inside. So ideally, we can see a line along the diagonal, which means it is perfectly calibrated. If this line goes beyond the diagonal, because we do bootstrapping in our calibration and wants to be conservative, so above diagonal means that we are a little bit more conservative than needed, but it's acceptable. However, if this curve falls below the diagonal, it means that we are over-assigning evidence and we might overdiagnose a patient, so which is less plausible. Okay, let's see some result. And this figure comes from the ClinVar 2019, ClinVar 2020. So that's exactly the same data set in the Klingen's calibration paper. And I try to post the 4 best single tools and their evidence strengths here. And we use P-KNN to joint calibrate all the 13 commonly used tools within that dataset together and find that P-KNN leads to a stronger evidence. And if we want to stick to the Klingen's point-based framework of ACMG guideline, then we can see that P-KNN still can assign the most number of pathogenic evidence to pathogenic variant and the most number of benign variant to benign evidence to benign variant, comparing to the 4 best tools in the dataset. More importantly, the P-KNN calibrated posterior probability seems to be very well quality. However, if these 4 tools are calibrated individually, we usually see some segment that the calibration is actually miscalibrated. We also want to test the generalizability of P-KNN. So we select 4 historical time points and use the tools available at that time, and we get it from DB and SFP of different versions, and integrate them with P-KNN. As we can see the result, with new tools are added into the framework, we can see the evidence gradually become stronger. And with the most updated variant effect prediction toolset, we have comparable or actually a little bit weaker pathogenic evidence and much stronger benign evidence comparing to the best single tool, which is AlphaMinSense. we currently have. And if we use Klingren's point-based score, then we can see that PKN actually assign a little bit more evidence than alpha missense to pathogenic variant, and apparently more benign evidence to benign variant comparing to alpha missense. And all these 4 tool sets are well calibrated, and alpha missense is also calibrated well. Okay, so that's the first part about joint calibrating multiple computational tools. But we not only have multiple computational prediction tools, but also have multiple lines of evidence. So for example, we have computational tools and experimental measurement. In the current Klingren's proposal for the next version of ACMG guideline, we tend to add the log likelihood ratio of predicted effect, which is in silico prediction tools, and experimental result. And this summation had a hidden assumption that these two evidence should be independent to make this summation viable. So our second question will be, when integrating these two types of evidence, does joint calibration play a role, or this evidence summation work well? So to show this, we use all the BRCA2 variants in the ClinVar database. And so here, each dot is a variant, and the red one are pathogenic, blue one are benign. The x-axis is a score given by demutational scan done by Dr. Sahu, which is published in Nature last year, and the y-axis is each variant's alpha missense score. As we can see here, the demutational scan separates pathogenic and benign score very well, except for one variant which is known to be benign. But alpha missense, although it separates blue and red dot less well, it seems can differentiate this benign variant. So if we only use deep mutational scan as a single tool for calibration, we use a one-dimensional window, and if, for example, our variant of interest is here at the tip of the arrow, we inevitably include this dot, and then the evidence and the purity of neighborhood will be the neighborhood of its purity. The neighborhood of this variant of interest is less pure, and therefore the evidence update or evidence strength is weaker. However, if we jointly calibrate these two tools, now our neighborhood is in this shape, and we can avoid contamination by this variant, and we have a more pure neighborhood and higher evidence strength. So that's exactly what we see. If we calibrate alpha missense alone in these BRCA2 variants, this is the evidence strength. And if we calibrate the mutational scan, this is what we got. And if we joint calibrate these two, we got much stronger evidence, and actually even stronger than direct summation of these two tools, which is the evidence summation proposal. More importantly, joint calibration gives an adequately conservative evidence assignment. So this calibration line goes beyond the diagonal line. However, if we directly sum the evidence, we have multiple regions of miscalibration. And even if we do evidence clipping and also use also integer base, even if we do evidence clipping for each single evidence before added together, we still get a large segment of miscalibration. So this suggests that PKN might play a role in integrating experimental prediction, and computational tools. And we do similar tests with all TP53 variant in ClinVar. So now this x-axis is a deep mutational scan evaluating the dominant negative effect, and the y-axis is ESM1B score. And as we can see again, joint calibration can lead to stronger evidence comparing to each tool calibrated individually. And also, joint calibration leads to an adequately conservative evidence assignment, while the guideline-based evidence summation leads to region of miscalibration. Oh, that's all I want to present today. And in summary, PKN can joint calibrate any combination of pathogenicity prediction tools, and it can produce more reliable and stronger evidence than calibrated individual predictors. And it can seamlessly incorporating new predictors as they emerge. Also, PKN may help integrating functional and computational evidence. And finally, I would like to go back to the questions. So, how should we use multiple variant effect prediction tools in clinical practice? Should we stick to the blindly selecting one tool, or should we try to use them together? Should we open to using them together? And the second question, how to extract stronger and more accurate evidence from these calibrated prediction? Should we use integer point-based score, or should we, if we can calibrate it very accurately, use the continuous evidence score? And should we stick to evidence summation or try to do joint calibration if we could? And finally, I'm curious, are these presented evidence convincing enough to support joint calibration as a viable option in clinical guideline for integrating multiple computational tools and for integrating computational tools and experimental measurements? And thank you very much for your time and listening.